Welcome to the webinar titled Acceptance Sampling Using Statgraphics Centurion. I'm Neil Paulhemus. I'll be doing the webinar today on a beautiful spring day here in Virginia. I hope it's as nice wherever you happen to be. Today's topic is acceptance sampling. The situation is this. Let's suppose that we've produced a lot or a batch of capital N items. We wish to make a decision about whether to accept or reject the lot based on a statistical sample. So we're going to take and inspect or measure a subset of the items in the lot, and based on that sample, make the decision either to accept or reject. In Statgraphics, the acceptance sampling procedures are contained under SPC on the main menu. The outline for today's webinar covers 4 basic approaches to acceptance sampling. The first approach involves the construction of OC, AOQL, or LTPD plans. And I'll be talking about each one of those as we go along. The second approach is to use one of various established standards. The ANSI Z1.4 or Z1.9 standards, which were derived from earlier military standards 105E and 414. Statgraphics also allows you to construct acceptance sampling plans using MIL Standard 1916. And finally, you can construct acceptance sampling plans based upon what's called sequential sampling. There are different types of acceptance sampling, and we'll be looking at 2 basic types. The first type is attribute sampling. In attribute sampling, you select items from the lot and inspect them. You don't measure anything, but you examine the items, and based upon that examination, classify each item as acceptable or unacceptable, good or bad. In that case, the acceptability of the lot is based on the proportion of unacceptable items in the sample. The second approach to acceptance sampling is called variable sampling. In variable sampling, you select items from the lot and take each item and measure some critical characteristic. You then take the measurements on all of the items in the sample and calculate the mean and standard deviation. The acceptability of the lot is determined by how close the mean is to the specification limits. We also need to talk about several different types of sampling methods. The first type of sampling we'll be looking at is single sampling. In single sampling, you inspect or measure lowercase n randomly sampled items from the lot. You then accept or reject the entire lot based on that one sample. Now, this is in contrast to double or multiple sampling, in which you take more than one sample. In a typical double sampling plan, you'd select the first sample and inspect or measure each of the items in that first sample. You would accept or reject the lot based on the first sample if, in fact, that sample showed the lot to be either very good or very bad. If the results were inconclusive, you'd go and take an additional sample and accept or reject the lot based upon the 2 samples combined. In a multiple sampling plan, you might take a third, a fourth, a fifth, or even more samples until you've accumulated enough information to make a decision. We'll also be talking about continuous sampling. With continuous sampling, you inspect or measure items continuously sampled from the lot. This sampling scheme then determines, based upon how good the initial results are, how frequently you need to sample it. Very good for a continuous process in which you're making many, many items. Finally, we'll also talk about sequential sampling. In sequential sampling, you inspect or measure randomly selected items one at a time. You go out, for example, and take a first item, examine it, and based upon the information you have, either accept the lot, reject it, or decide to select another item. And I'll be showing you toward the end of the webinar an example of sequential sampling. Now, the first example we want to look at is a single sampling plan for attribute data. With this sort of plan, what we do is we take a sample of size n, lowercase n, from a lot containing capital N items, and we inspect each item. We'll let X be the number of unacceptable or non-conforming items, items that don't meet our requirements for that particular product. If X, the number of non-conforming items, turns out to be less than or equal to some number C, we'll accept the lot. In that case, C is called the acceptance number. If X is greater than C, we'll reject the lot. Now, if a lot is rejected, it's either going to be returned to the manufacturer for rework, or will be rectified using 100% inspection. If we rectify a lot, we actually go through and inspect every item in the lot. And if it turns out to be defective or non-conforming, we'll replace it with a good item. Okay, now we need to go to Statgraphics and call up our first acceptance sampling procedure. So let me toggle over to where I'm running Statgraphics and call up the first acceptance sampling procedure. To do that, I'll go to SPC, and you'll see a section for acceptance sampling. There's acceptance sampling for attributes and acceptance sampling for variables. I'm going to start at the top with acceptance sampling for attributes and select the item OC, AOQL, LTPD plans. This will bring up a dialog box on which I need to select, first off, the type of plan that I want it to generate for me. Now, let's talk about the first choice on that list, the OC plan. Okay. There are basically three types of plans being offered to us here. The first type of plan is an OC, or operating characteristic plan. To generate such a plan, we need to input two values. We need to input a producer's risk and a consumer's risk. The producer's risk is the risk that I will, based upon my sampling plan, reject a good lot. And by a good lot, we'll mean a lot that's producing no more than AQL non-conforming items. Now, what AQL stands for, well, there's two definitions. It's sometimes called the acceptable quality level, or it may be called the acceptance quality limit. Whatever it's called, it's the poorest level of quality that the consumer finds acceptable on average. Okay? And what we will do is we will make sure, for the producer's sake, that we don't reject lots operating at the AQL very often. We also need to control the consumer's risk, and we control the consumer's risk at the LTPD. The consumer's risk is basically the risk that we will accept a poor lot. Now, it's controlled at the LTPD, which stands for lot tolerance percent defective. The LTPD is the poorest level of quality that the consumer is willing to tolerate in any lot. AQL is the poorest level of quality the consumer accepts on average. The LTPD is the poorest level of quality that the consumer is willing to tolerate in any given lot. Now, let's go back to Statgraphics. We're going to start here by creating an OC plan. And let's suppose that we are producing a lot with 5,000 items. Or we've probably already produced it. We're going to take a sample from it. Okay. The producer's risk is currently set at 5% at the AQL, and I'm going to put in for an AQL 1%. I'm going to assume that the worst quality I want to see on average is 1%. I'll also set the consumer's risk, the beta risk, at the LTPD at 10% when, in fact, the lot contains 3% defective items. So I'm controlling the producer's risk at the AQL and the consumer's risk at the LTPD. I'll then press OK, and there are a number of different charts that I can create, so I'll ask it to create all the different options. Now, this will open up an analysis window, and you will see in this section over here the acceptance sampling plan that it generated. It's telling me that I need to take a sample of 384 items from the lot and accept the lot if I see 7 or less non-conforming items. 7 or less non-conforming items, I will reject the lot. Accept the lot. 8 or more non-conforming items, I will reject the lot. That actually gives me a producer's risk of about 3.5% at the AQL and a consumer's risk of about 9.98% at the LTPD. Now, because of the discrete nature of the items, I have an acceptance number of 6 or 7 or 8. It's an integer. I can't get exactly the alpha and beta that I specified on the dialog box. But it'll find the smallest plan, the smallest sample size, that gives me no worse alpha and beta risks than I ask for. Okay, now, there are a number of different graphs that are important to look at here. The first graph that's important to look at is the operating characteristic curve, the OC curve. That's where the plan gets its name. The operating characteristic curve plots the probability that I will accept the lot as a function of the true percent of defective items in that lot. Now, basically, I have created a sampling plan by specifying 2 points on this graph. I've told it that at 1% defective items, I didn't want to reject the lot more than 5% of the time. That was the producer's risk. So the curve hits 95% at 1% defective. The consumer's risk determines this particular point down here, and I told it I wanted a 10% risk of accepting the lot if in fact the percent defective was 3. So the program has figured out that I need to take a sample of 384 items with an acceptance number of 7 in order to achieve those consumer and producers risks. Okay. Now, another graph that's quite interesting is this graph right here. It's called the AOQ curve. It's the average outgoing quality. Now, what the average outgoing quality curve shows me is, on average, the percent of defective items that the sampling plan will accept as a function of the true percent defective in the lot. Now, the AOQ is assuming that rejected lots will be rectified. So it assumes that if I have a bad lot, I will inspect every item in the lot and replace it with a good one. That's why eventually, if the lot is bad enough, the percent defective actually goes back down. You see, if it's good, I'll be accepting most of the lots, and I'll be getting whatever percent defective is in the lot. If it's very bad, I'll be rectifying most of the lots, so most of the lots will have 100% good items. The point at which the AOQ is the highest is called the average outgoing quality limit. Okay, it's the highest AOQ, which in this case is about 1.1, about 1.1%. Okay. You can also see that, incidentally, back here on the output. It says the average outgoing quality limit, the AOQ, was 1.09% at 1.5% defective. One final graph in statistics that's interesting here is the average total inspection. Okay. Assuming that I will rectify the lots, this graph shows me on average how many units I will end up inspecting. It turns out that the lot is very good. It will be accepted most of the time, and I'll be inspecting only 384 items. That's this line down here. If the lot is very bad, however, I'll be rejecting almost every sample and therefore inspecting 100% of the lot most of the time. Okay, that's in OC plan. Now, there are two other plans that Statgraphics will generate for you. Let me go back to my PowerPoint slides here and talk a little bit about a couple other plans. The second type of plan you can ask Statgraphics to generate is an AOQL plan. In an AOQL plan, you actually input the desired average outgoing quality limit. Okay, that is the worst average outgoing quality limit you're willing to tolerate. You also tell it the percent defective at which you would want to minimize the amount of inspection. Now, to do that, I can go back to Statgraphics, go back to my input, and tell it that I'd rather have an AOQL plan. And down here, I tell it what the desired features are. I can tell it that on average, I expect to see, let's say, 0.5% of defective items. Okay, and it will minimize the average inspection at 0.5% defects. I can also tell it that I'd like an average outgoing quality limit of 1%. I then press OK, and it tells me, well, in that case, take a sample of 189 and use an acceptance number of 3. Or finally, there's a third type of plan I can ask for, and that is an LTPD plan. An LTPD plan is a plan where you specify both the percent defective, where you want to minimize the inspection, and the consumer's risk. And that'll give you another sample size and another acceptance number. Okay, well that's a very typical acceptance sampling plan if you have attribute data. How about if you have variable data? How about if instead of simply inspecting the items, you want to measure each of the items? Let me show you a typical sampling plan for variables. The way it works is the following. I'll start off and I'll take a sample of lowercase n items from the lot. Okay. I'll measure each of the items. I won't just inspect them. I'll actually measure some critical characteristic, the weight or the strength or something like that. Okay. Based upon the n measurements, I'll compute the sample mean and the sample standard deviation. I'll then calculate a z-score against each of the specification limits. I'll take the difference between the mean and the lower spec divided by the standard deviation, and the difference between the upper spec and the mean divided by the standard deviation. Okay? If either of those z-scores is too small, I will have to reject the lot. Or in particular, if both z-scores, the one against the upper spec and the one against the lower spec, are greater or equal to some critical value k, I can accept the lot. Okay, but if either z is less than or equal to k, okay, I will reject the lot. Okay, rejected lots are, as in the attribute sampling case, returned either for rework or they're rectified. Okay, now let's take a look at how Statgraphics does this for variable data. It's very similar to attribute data. Let's go back to Statgraphics for a moment. In this case, we'll go to SPC acceptance sampling variables. I'll tell it I want an OC AOQL LTPD plan. And you see a dialog box that's similar to the one we saw before. Let's tell it we want an OC plan. We have a lot size of 5,000. We want a producer's risk of 5%, a consumer's risk of 10%. The AOQL will be 1. The LTPD will be 3. There's one additional characteristic that I also have to specify, and that is, what are we going to do about the standard deviation of the measurements? We can either assume we know what sigma is, or we can use an estimate from the sample. I'm going to select use an estimate from the sample, and then I'm going to press OK. All right. Well, now it's going to allow me to generate various types of tables and curves, and I'll just go ahead and press OK. And you will see that in this case it says take a sample of 137 items and compute the z-scores. If either z-score is less than or equal to 2.07592, reject the lot. If the z-score against both specification limits is greater than that, then we can accept the lot. So you can see that this acceptance plan takes into account the distance from the mean to the specification limits divided by the standard deviation. Okay. That's a typical acceptance sampling plan for variables. Okay, well, that's the first type of plan I wanted to show you, the OC type plans. The second type of plans we want to talk about are those developed initially by the United States Department of Defense and later picked up by ANSI as standard acceptance sampling plans. The third example in the webinar is actually going to be a sampling plan for attribute data following the ANSI Z1.4 standard. Now, these ANSI Z1.4 is intended primarily for inspecting a continuing series of lots or batches, not just a single lot or a single batch, but a whole continuing series of lots or batches. The ANSI Z1.4 specification gives a procedure for determining sample sizes for what's called normal, tightened, and reduced sampling. The normal sampling is where you would start out. Okay, and it gives a particular sample size. If in doing the sampling, it turns out that you start rejecting a lot of lots, there's a rule for when you need to switch to what's called tightened sampling. Tightened sampling typically requires a larger sample size. On the other hand, if you're doing normal sampling and things are very, very good, you're never rejecting any lots, there's a rule for when you can switch to reduced sampling. That's smaller sample size. If you've proven that your process is producing very good lots, you don't need to take as big samples. Now, the ANSI Z1.4 standard can be used either for controlling the percent of non-conforming items, that is, where you take an item and classify it as either good or bad, or for non-conformities per unit. Non-conformities per unit is where you might take a look at an item and identify the number of non-conformities in that item. An item may actually have more than one non-conformity. In that case, the Poisson distribution is appropriate. Okay, now let's take a look at the data input dialog box and see what we get if we ask for ANSI Z1.4. Okay, so I'm going to go back to Statgraphics. Here I'm going to go to SPC, acceptance sampling, attribute data, and ask for military standard 105E. It uses the equivalent sampling plans as ANSI Z1.4. Now, the first thing I'll need to tell it is what I'm worried about. Am I worried about percent non-conforming or non-conforming per unit? Well, I'll assume that I'm worried about the percent of non-conforming items. I'll also tell it the lot size, and now it gives you different ranges of lot sizes. So if I assume I have a lot of 5,000 items, I'll select the range of the lot sizes that contains 5,000. There are also different inspection levels. There are inspection levels 1, 2, 3, S1, S2, S3, and S4. The inspection levels are typically determined ahead of time by contract and depend upon how critical the characteristic is that you're monitoring. The default level is 2. If it's a very critical characteristic, you might want to go to 3, which would require larger samples, or if it's really not that critical, reduce it to 1. I'll just keep it at a default level of 2. The third thing you need to specify is the AQL, the acceptance quality limit, and there are a whole different range of values, everywhere from 0.01% up to 10%. I'll select 1%. Here is where I tell it whether I want reduced, normal, or tightened inspection. And finally, I can ask for either single sampling, where it'll take a single sample, double sampling, or multiple sampling. Okay, let's start with a single sample. Let's press OK, OK again. And you will see right here the derived sampling plan. A lot size of 5,000, inspection level 2, AOQL of 1%. Normal inspection says take a sample of 200. The acceptance number is 5. The rejection number is 6. If you take a sample of 200, if you see 5 or less non-conforming items, accept the lot. 6 or more non-conforming items, reject the lot. Okay. That's single sampling. Well, how about if I wanted to do double sampling instead? Let's see what I get if I do double sampling. Well, double sampling starts out by taking a sample of 125 items. I take a sample of 125 items. If I see 2 or less non-conforming items, I'll accept the lot. 5 or more non-conforming items, I'll reject the lot. If it's between 2 and 5, meaning it's either 3 or 4 non-conforming items, I'll take a second sample, another 125 items sampled from the lot, randomly sampled from the lot. In the combined sample of 250, if there are 6 or less non-conforming items, I'll accept the lot. If there are 7 or more non-conforming items, I'll reject the lot. Now, the interesting thing about double sampling is that on average, you actually are inspecting less items than if you did a single sample. For example, here is a chart, what's called the average sample number, or ASN curve, which shows me on average how many items I'll sample from the lot as a function of the percent of non-conforming items in the lot. You'll see it peaks around 175. Okay, somewhere around 3% defective items, I'll end up sampling 175 items on average, meaning that very frequently I'll have to take a second sample. Remember, the choice was either single sample, take 200, or in double sampling, take 125, and if necessary, take another 125. Well, on average, it turns out you can get away with sampling smaller numbers of items if, in fact, you use a double sampling plan. Now, I could also ask for a multiple sampling plan. A multiple sampling plan works like this. You take a sample of 50 items. Based upon the first 50, you're not allowed to accept the lot. But if you see 4 or more bad guys, you reject it. Okay, less than 4, you take another sample of 50, and in the combined sample of 100, 1 or less non-conforming items, you can now accept the lot. 5 or more non-conforming items, reject the lot. And for this particular plan, you keep taking samples of size 50 if necessary until finally you've taken a 7th sample, gotten 350 items altogether, at which point if you have 9 or less non-conforming items, reject the lot. 10 or more non-conforming item, 9 or less non-conforming items, accept the lot. 10 or more non-conforming items, reject the lot. My head's thinking faster than my mouth is working. 9 is the acceptance number, 10 is the rejection number. You can see on average, you sample no more than about 160 items. Okay. That is military standard 105E, also known as ANSI Z1.4. All right. The fourth example I wanted to talk about, example number 4, is the ANSI standard Z1.9 for variable data. ANSI standard Z1.9 is derived from the original military standard 414, which was also developed by the U.S. Department of Defense. Like Z1.4, it's intended primarily for continuing series of lots and batches. It has sample sizes for normal, tightened, and reduced sampling. The one thing different than the attribute sampling, because we're dealing with measurements now, will be an assumption that the measurements are characterized by a normal distribution. Okay. Well, let's go over to Statgraphics and see how military standard 414 ANSI Z1.9 works. I'll go to SPC, Acceptance Sampling Variables, and select military standard 414. The first thing I need to specify, as I always do when I'm sampling for variables, is whether I know sigma or I'm going to estimate it. And as before, I'm going to tell it here that I don't know what the sigma is. I'll pick a lot size, and I'll find here a lot size that contains 5,000. I pick the inspection level that I want, and I'll take the default. I pick the AQL, the acceptance quality limit. I'll set it at 1.0, and the type of inspection will select normal. Now, when I specify OK, the next thing I'm going to see is a dialog box. It's a little different than we've seen before. A dialog box asking me what I want to do. Do I want to determine the sample size, or do I want to analyze the results? Since this is a little more complicated than the others to do the calculations, the program, as you'll see in just a moment, actually allows you to analyze the data as well as determine the sample size. Okay. However, we will start by telling it we'd like to determine the sample size, and it's going to tell us right now that what we need to do is take a sample of 75 items. We'll take a sample of 75 items, compute the mean and standard deviation. And then we will estimate, assuming a normal distribution, what percent of the items in the lot are outside of my specification limit. If it's 2.27% or less, I'll accept the lot. However, if I estimate that more than 2.27% of the items in the lot are outside the specification limit, I'll reject the lot. Okay, well, let's do an example. Let's suppose, okay, that we have a specification of on our product that is 200 plus and minus 10. Maybe this is tensile strength, and maybe we're measuring pounds per square inch, and the acceptable range is 200 plus and minus 10. What I'm going to do is I'm going to generate 75 random numbers. I'm going to generate 75 random numbers from a normal distribution with a mean of 204 and a standard deviation of 2. 75 is the sample size it told me I needed. I'm then going to have the program analyze the data and tell me whether or not my lot is acceptable. Okay, so let's go back to Statgraphics, and let's go to the data sheet. So far, there hasn't been anything in the data sheet. I, however, am going to calculate a column which I'm going to call X. Okay? And in that column, I'm going to right-click, go to generate data and type R normal. That's the Statgraphics operator that I talked about in one of the recent webinars. I'll type R normal open parens 75, 204, 2 close parens. That says generate 75 random numbers from a normal distribution with a mean of 204 and a standard deviation of 2. There they are, 75 random numbers from a normal distribution. Okay? Now I'm going to go back to the ANSI Z1.4 analysis. I'm going to go to the dialog box, and I'm going to tell it, in this case, that I'd like to analyze the data sample. And the sample I want to analyze is in the column called X. Incidentally, instead of giving it the data, I could have just given it the mean and standard deviation, but it's easier to have it analyze the entire data. I'll also put in my specification limits, which in this case go from 190 to 210. It was 200 plus and minus 10. And now what the program is going to do, it's going to analyze the data. Okay, and here now you can see the analysis that it's done. First off, it's computed z-scores, which the table calls quality indices. The z-score against the lower spec was 6.18. The z-score against the upper spec was 2.88. Okay? From those z-scores, I estimate the percent of the lot that doesn't conform to the spec. And in total, I'm estimating in this case that only 0.154% of the lot do not meet the spec. Since that's certainly not bigger than 2.27%, I accept the lot. Okay. So the nice thing about the Statgraphics procedure here, you see, is that not only will it tell you how many samples you need to implement Z1.9, it will go ahead and tell you on any particular data set whether to accept or reject the lot. Okay, and the reason we do that here is we're obviously having to integrate a normal distribution to figure out the estimated percent of non-conforming items. Okay, now those are the original military standards, 105E and 414. There's a later military standard that's also in wide use called Military Standard 1916. Military Standard 1916 consists of 3 matched sampling plans. There's a sampling plan for attributes, and they're all, incidentally, C equals 0 plans. They're all plans where the acceptance number is 0. There are also plans for sampling by variables, which is based not only on the z-scores that we just looked at, but also by a new F criterion. And there's also a continuous sampling plan for attribute data. Now, let me show you an example of Military Standard 1916. Let's go back to Statgraphics. Let's go to SPC, Acceptance Sampling, Attributes, Military Standard 1916. I'll pick the lot size I want, in this case the range containing 5,000. For Military Standard 16, there are 7 verification levels. They are each related to different AOQs. Okay, the sort of middle level that I'm going to choose is verification level 4. You can also pick normal, reduced, and tightened inspection, and there are rules for switching back and forth. Okay. If I press OK, the analysis will show me two sampling plans. It will show me a single sampling plan and a continuous sampling plan. The continuous sampling plan says go out and take 160 items, inspect 160 items. Accept the lot if you see 0 non-conforming items. If you see 1 or more, reject the lot. It's a C equals 0 sampling plan. Okay. You'll notice it's a little bit smaller than the one generated by the ANSI standard Z1.4, I believe. Okay. You can also see over here the operating characteristic curve. And incidentally, all of these C equals 0 plans have very sharp drop-offs. You can see, for example, if there is only 1% of defective items, there's maybe a 20% chance, that's it, of accepting the lot. C equals 0 acceptance plans have a very sharp OC curve. It's just one of their features. The second plan that I'm offered is actually a continuous sampling plan. This is very nice, a continuous sampling plan, if you're generating items continuously. A continuous sampling plan consists of a screening phase and a sampling phase. The screening phase is where the sampling plan starts. And in this case, it says, when you start producing these items, inspect the first 815 items. Okay. If you see any bad ones, start it all over again, inspect the next 815. However, if you get through 815 items and they're all good, then you can start inspecting only 1 out of every 34. That's called the sampling phase. And you can continue to inspect 1 out of every 34 as long as you don't see any bad items. As soon as you see a non-conforming item, you have to go back to the screening phase and then sample every item until you've seen 815 good ones, in which case you can switch back to the sampling fraction. That's an alternative continuous sampling plan that's offered by Military Standard 1916. There is also a Military Standard 1916 for variables. Very similar to Military Standard 1916 for attributes in terms of what it asks for. It'll ask for the lot size, the verification level, and the type of inspection. It's also similar to ANSI Z1.9 in that it uses z-scores to determine whether or not a lot is acceptable. It uses z-scores plus another F criteria. Now, I've written down actually the criteria that are used for accepting lots in Military Standard 1916 when you're dealing with variables. It works very similarly to the Z1.9 with respect to z-scores. I take a sample of items from my lot. I measure every item. I calculate the average. I calculate the standard deviation. I then compute a z-score with respect to the lower specification limit, a z-score with respect to the upper specification limit. And if the smaller of those two numbers is less than some k, less than or equal to some k, I have to reject the lot. So to that extent, it's exactly the same as Z1.4. There's a second criteria, though, that also applies if, in fact, you have two specification limits. Incidentally, this works, these z-score tests, if you have only one spec. You just calculate whatever z you have. That has to be greater than k. If you have two specs, however, you also calculate this thing called F. And F is the standard deviation divided by the upper spec minus the lower spec. And there's a maximum value that F is allowed to be. Okay? Well, let me show you one of these. Let me go back to Statgraphics real quick and show you how that all works. Let me go to SPC, acceptance sampling for variables this time, military standard 1916. I'll tell it I have a lot containing 5,000 items, verification level 4, normal inspection. As with Z1.9, I have a choice of either determining the sample size or analyzing the data. I'll ask it initially to determine the sample size. It says go out and sample 41 items from the lot. If all of your z-scores are greater than 2.63 and your F statistic is no more than 0.177, then you can accept the lot. Then you accept the lot. If Z is big enough and F is small enough, you accept the lot. Otherwise, you reject the lot. Okay? Well, let's go ahead, take the same data we had just a moment ago, go back to the data input dialog box, and tell it we'd like to analyze the data sample. Remember, I generated a data sample and put it in a column called X. Okay. Now, in this case, the sample size is a little smaller. I only need 41 items, so I'm going to tell it in the select field to just analyze the first 41. The specification goes from 190 to 210. Press OK. And down here, it will give me the results. It calculates z-scores of 6.08 and 2.76. They're both bigger than 2.63. That's good. It computes an F statistic 0.113. That's less than 0.177. That's good. So I accept the lot. Okay. That's an example of military standard 1916 applied to variable data. Good. Now, one more type of acceptance sampling I want to talk about, and that is sequential sampling. Sequential sampling is very useful if you're sampling very large lots. 5,000 is pretty large. But if you're sampling very large lots, the way sequential sampling works, it's actually quite similar to the OC plan that I started this webinar with. You start by specifying an AQL and an LTPD. The AQL, that's the worst quality you're willing to accept on average. The LTPD, that's the worst quality you're willing to accept in any lot. Okay. Like the OC plans, we will set the producer's risk alpha at the AQL. We'll set the consumer's risk beta at the LTPD. What's different here, though, is we are going to start and we'll inspect the items one at a time. We'll start sampling from this very large lot, items one at a time. After each item, okay, I will plot my results on a cumulative sum chart. So, for example, I'll inspect the first item. It's a good one. That's a 0. I'll take the second item. It's a good one. That's a 0. I'll take another item. That's a bad one. That's a 1. You actually plot the number of defects, you'll see this in a second, versus the number of items you've looked at. After each item, you decide either to accept the lot, reject the lot, or take another sample. Okay, now, my last example is one in which I'm going to generate some data and apply sequential sampling to it. In this case, I'm going to generate some data from a binomial distribution. Go generate some Bernoulli trials, if you like, where the probability of getting a defective item is 1%, 0.01. I'm going to do it similarly to what I did with the normal distribution, but in this case, I'm going to use an operator called R uniform. I'm going to generate 5,000 random numbers between 0 and 1. And then I'll use the Boolean expression less than or equal to 0.01. The uniform numbers, that'll be a number somewhere over the range 0 to 1. If it's less than or equal to 0.01, it'll be true, and I'll get a 1. If it's not less than or equal to 0.01, that'll be false, and I'll get a 0. And then I'll apply some sequential sampling to that. Okay. So let's go back to Statgraphics. Let's go back to the data book. Let's create a second column and call it item. In the item column, I'm going to press the right mouse button and tell it I'd like to generate some data. And this time I'm going to type R uniform, open parens, 5,000, comma 0, comma 1. That's 5,000 numbers randomly distributed over the interval 0 to 1. And then I'll do the Boolean expression less than or equal to 0.01 and say OK. You'll see that what it's done is it's generated a column of zeros and ones. Yeah, there are some ones here, not many, but there's one right there. A column of zeros and ones. Now, to decide whether to accept or reject this data, I'll go to Describe, Categorical Data, Sequential Sampling. Okay, this sequential sampling has other uses, so it's actually not under SPC, it's under Describe. Describe, Categorical Data, Sequential Sampling. The data I want to analyze are in item. Now, the dialog box that comes up, the second one, asks me, what do I want to test? There are sequential sampling plans for means, standard deviations, rates, and so forth. I want to analyze the binomial proportion. And it just reminded me that I need to enter a number between 0 and 1 for my null hypothesis. Well, to reproduce what we've been doing all day, I'm going to put in an AQL of 0.01, 1%, and set the producer's risk at 0.05, 5%. The alternative hypothesis is going to be the LPD of 3 with a consumer's risk of 0.10, 10%. That's the same as I've been doing before. I'm then going to press OK. Okay, and it didn't like something. Oh, I put in 3. I need to put in 0.03. It's a proportion, 3%. That's a little bit better. And now what it's done is created the following chart. It's given me a cumulative sum chart. Every time I've taken a sample, I've characterized it as conforming or non-conforming. The cumulative sum is the total number of non-conforming items that I've seen after I've looked at each sample. Now, the green region is the acceptance region. The red region is the rejection region. And let me go ahead and zoom in on this a little bit. I'll use my rubber band window actually to zoom that up a little bit so you can see what's happened. At the very beginning, I've got some negatives here, just ignore those. But at the very beginning, when I sampled the first item, it was good. The second was good, the third was good, the fourth was good, and so forth. Oops, here I had a bad item, so the cumulative count jumped to 1. The way a sequential sampling plan works is you plot these cumulative sums. Once they go into the green area, you stop and accept the lot. Once they go into the red area, you accept and reject the lot. However, as long as the continuous cumulative sum remains in the white area, not green or blue, you go out and you take another sample. So we go out and we take sample after sample after sample after sample after sample until my cumulative sum either goes into the green region or goes into the red region. Okay, in this case, we accept the null hypothesis at 385. After 385 samples, the cumulative sum went into the green region, and I accept the lot. Okay. Now, the nice thing about sequential sampling, let me go ahead and plot the average sample number curve, is that whereas a fixed size sample normally takes, on average, about 390 samples, a fixed size sample, to make a decision. Here, I can usually make a decision within about 200 to 300 samples. I got a little unlucky this time. It ended up being 385, something like that. On average, though, it should not have been any more than about 280. So on average, a sequential sampling plan will give you smaller sample sizes than a fixed sampling plan. Now, there will be occasions when it goes on and just stays in that white region. And normally you'll stop the test once you've gotten to maybe 3 times the fixed sample size plan. Okay. Well, let's go back, if we can, and just summarize what we've done. Okay. We have looked at a number of different plans during this webinar. And the plans are typically useful for different things. If I want to assure a particular level of quality for both consumers and producers, then I would typically select either an OC plan or a sequential sampling plan. If I wanted to assure a acceptably small average outgoing quality, I'd select an AOQL plan. If I wanted to assure that quality was no worse than some target level, I'd select an LTPD plan. If I wanted to maintain quality at a particular target, I'd pick one of the military or ANSI standards to use. This summary, incidentally, comes from Doug Montgomery's book, and I'll give you the reference in just a moment. So depending upon what my major goal was, am I looking at a single lot? Am I looking at a whole continuous set of lots or batches? I could use one or the other of these acceptance sampling plans. Now, I'm going to put on our website both the recording of this webinar and also my PowerPoint slides. I'll show you in just a moment how to get there. As part of the PowerPoint slides, I have given you the basic references here. I've given you the references for the standards, the military standards, and also the ANSI documents, documenting, in addition to how we derive these sampling sizes, the rules between switching between normal, tightened, and reduced inspection. I've also listed on this screen 3 excellent textbooks that you might want to refer to having to do with acceptance sampling. Edward Schilling and Dean Neubauer have a book called Acceptance Sampling and Quality Control. Doug Montgomery has a chapter on acceptance sampling in his book on quality control. And Stevens also has a book that talks all about acceptance sampling plans. So if you're into acceptance sampling, these are the references you ought to be referring to. Now, finally, before I answer some questions, if you want more information, if you want to download the PowerPoint slides, if you want to watch the video again, I doubt that, but maybe you want to refer the video to someone else, either go to www.statgraphics.com and go through the sequence, watch a video, go to video, watch another video, and you'll get to a page with lots of videos and also the last several webinars. Or go to YouTube and search for Statgraphics Acceptance Sampling, and we'll get this webinar up on YouTube probably sometime this afternoon. All right, again, I thank you all for your patience. Let me go ahead now and look at the questions that came in. Oh boy, quite a few. And hopefully I'll be able to answer quite a few of these questions. Okay. Give me just a moment where I can figure out how to get enough space to see the questions. Okay, here we go. Question number 1. For variable sampling plans, is it necessary to check for normality requirements prior to applying the variable plan? Well, that's certainly something you should be doing. The K criteria or the M criteria on the variable plans depend on estimating the proportion of items outside the specification limits. That is completely dependent on the assumption of normality, so the answer is clearly yes. You should be confident that your measurements come from a normal distribution, or that you can transform the measurements so that they are approximately normal before using those variable plans. And that's a good point. It definitely is dependent on the assumption of normality. Second question, why do you mention the military standard? It has been officially retrieved and is now obsolete. Z1.4 and Z1.9 are the substitutes. The sampling sizes are exactly the same, whether they be military standards or the ANSI standards. Actually, I call them both on the menu. I call them both Military Standard 105E and Z1.4. As far as the sample sizes are concerned, they came from Military Standard 105E, so I tend to refer to that. And a lot of people are still familiar with that nomenclature. So we can call them whichever we want. The Z1. Here's another question. The Z1.4 has multiple sampling plans of 7 consecutive samples. The ISO 2859 have plans of only 5 consecutive samples. To my knowledge, there is a difference between those multiple sampling plans. Okay, I will have to look into that. I did not realize that was the case. I know certainly the single sampling plans are the same. I will double check on the multiple sampling plans and see if in fact there is a difference, in which case I guess I'll have to put an option in for which one you want to use. Are the military, here's another question, are the military and sequential sampling plans new additions to the present Statgraphics? Yes. Well, no, the military one is, the sequential one is not. Version 16 had all the original OC, AOQL, LTPD plans. They've been around for a while. We've had the sequential sampling since version 16. The military/ANSI plans are new to 17, version 17. Another question, what's the criteria to establish good values for alpha and beta? Well, that's a good question, isn't it? We tend to pick numbers like 5% and 10% as defaults because we tend to be 95% people or 90% people. What is a good value? Well, that would really depend upon the problem, wouldn't it? How often are you willing to make a mistake about rejecting a good lot or accepting a bad lot would depend, I suppose, a lot on the consequences of accepting a bad lot or rejecting a good one. That's definitely an engineering judgment. What the AOQL should be, what the LTPD should be, and what the alpha and beta risks should be. You know, we've set it up typically with a default of 5% for each. I changed the consumer's risks just basically to show you that you could change it. It will affect the operating characteristic. It will affect how often you make a mistake. It will also affect the sample sizes. All that typically has to be worked out ahead of time, as is the verification level. And the verification level definitely affects the sample size, typically negotiated by contract. Okay, well, there weren't quite as many questions as I expected today. I hope you enjoyed the webinar. We will get both the slides and the video posted sometime this afternoon. Any other questions, you can send it either to support@statgraphics.com or directly to me, Neil, at statgraphics.com, and I will get back to you. Thanks again.